While probability theory has a long history, as explained in the previous video, its transformation into a science began during the Renaissance. An important moment arrived in 1657 when Christian Huygens published his treatise on reasoning in games of chance. This foundation was further strengthened by Jacob Bernoulli, whose work, The Art of Conjecturing, expanded the horizons. However, probability is only one side of the coin. On the other side lies statistics, the art of gathering, analyzing, and drawing inferences from data. While probability grew from the logic of games, statistics has more pragmatic roots. The systematic tracking of population and economic wealth, often for taxation or military readiness, stretches back to the dawn of antiquity. While the theory of probability was being refined in the 17th century, the practical application of statistics, known as the science of the state, had already been in use for millennia. Early rulers understood that to govern effectively, they needed to quantify their power. One of the earliest recorded of census is found in the Bible, specifically the Book of Numbers. These censuses were conducted to determine the number of men fit for military service and to organize the distribution of land among the tribes. Emperor Augustus took the census to a new level of sophistication. He maintained the Breviarium Totius Imperii, a summary of the whole empire, a massive inventory that tracked the number of citizens, the strength of the Roman legions, the fleet, and the amount of revenue in the public treasury. Moving forward, following the Norman conquest, William the Conqueror commissioned the greatest survey of medieval England. Known as the Domesday Book, written in the 11th century, it recorded the ownership, value, and resources of every piece of land in the kingdom, providing a definitive statistical record for taxation and control. Significant statistical investigation began when merchants needed probabilistic estimation of events. Insurance companies in particular invented the concept of shared risk to protect merchant vessels. The concept of insurance seems to have been created as early as Roman times to protect the ships. However, these kinds of evaluations were made more based on intuition. The shift toward a mathematical foundation began in the 17th century with John Grount. The insurance companies needed some mathematical determination of probabilities. Grount drew statistical inferences from analysis of mass data. He used reports of yearly and weekly burials and christenings in various London churches in order to keep track of plague. In 1662, his natural and political observations made upon the bills of mortality was groundbreaking. Grount's work included conclusions on validity of inferences and generality. It was the first time someone used mass data to draw inferences about life expectancy and population trends. Building on Grount's foundation, the famous astronomer Edmund Halley published An Estimate of the Degrees of the Mortality of Mankind, 1693. Halley applied these statistical methods to the pricing of annuities, creating the world's first scientifically calculated life table. The work of early pioneers was carried on by Abraham de Moivre, a French Huguenot living in London. In 1718, he published The Doctrine of Chances, the first major textbook on probability in English. It was a landmark for the mathematics of permutations and combinations. Later on, he published Annuities upon Lives in 1725, where he noticed the connection between probability and life insurance, introducing a linear model for mortality that simplified the complex calculations required for insurance prices. After de Moivre, probability and statistics entered a transformative era, evolving from a collection of gambling strategies into a rigorous branch of mathematical analysis. This shift was fueled by the maturation of infinitesimal calculus, pioneered by Newton and Leibniz. Bernoulli showed how it could apply to probability with his law of great numbers that provided important insight to this science for the time. He proved that as the number of independent trials increases, the observed average will converge toward the theoretical probability. This established the first mathematical link between theoretical chance and real-world data. By the mid-18th century, Leonhard Euler began to organize and systemize the field. He moved away from analyzing specific games of chance and instead treated probability as a general branch of analysis. He solved complex problems related to the Genoese lottery and laid the groundwork for managing observational errors in scientific data. Toward the end of the 18th century, Joseph Louis Lagrange revolutionized the field by applying differential calculus to probability theory. He was one of the first to use calculus to analyze the distribution of errors in physical measurements. It allowed scientists to determine the most probable true value when multiple measurements of the same object differed. It was a crucial step in the birth of modern scientific statistics. The 19th century marks the transition to the modern era probability. The figures that dominated, like Pierre-Simon Laplace, unified the field and shifted the focus to more complex problems. Now the problems studied were not of discrete outcomes, but of an infinite number of outcomes, such as those found in physical measurements. Laplace developed tools to handle these kinds of problems, developing this way the theory of continuous probability. Laplace's influence extended beyond mathematics. Even though he was more invested in astronomical events, he did teach Bonaparte for a period of time at the École Militaire, and later briefly served as his Minister of the Interior. He then used the theory of probability to develop a statistical measure of reliability so that he could define whether astronomical phenomena was because of definite physical causes or because of pure chance. He published in 1812 Analytical Theory of Probability. It was in this work that he introduced the central limit theorem, arguably the most important theorem in statistics, which explains why the bell curve appears so often in nature. Laplace is called the father of modern probability theory. Following Laplace and his contemporary Carl Friedrich Gauss, the 19th century saw the derivation of various mathematical distributions that allowed scientists to model different types of data. The final chapter in our timeline moves from the realm of state and physical errors into the study of humanity, biology, and complex systems. In 1829, Adolphe Quetelet, a Belgian astronomer, applied statistical analysis to census data, pioneering the field of social physics. He introduced the concept of the average man, suggesting that human traits and behaviors follow the same mathematical laws as the stars. Further on, Father Gregor Mendel, an Augustinian friar, related probability to genetics. He demonstrated that the inheritance of traits followed specific probabilistic laws. He laid the foundation for modern genetics, showing that heredity was not a blending of parents, but a predictable mathematical outcome. In 1877, Francis Galton, a polymath and cousin of Charles Darwin, discovered the law of regression to the mean. While studying the heights of parents and their children, he developed the correlation coefficient, a tool that allows us to measure the strength of the relationship between two different variables. In 1894, Carl Pearson, building on Galton's work, applied probability to biology and founded what we know as biometrics. He also created the chi-squared test that is widely used in modern medical research. By the end of the 19th century, the Russian mathematician Andrei Markov developed his chain theory of probabilities, where described sequences of events where the probability of the next event dependent on the current state. In the 20th century, we have Norbert Wiener, that expressed his belief on probability being the link between physics and mathematics, founding this way cybernetics. He studied the communication and control in living beings and machines, proving that random noise could be managed through statistical feedback loops. We will explore these concepts following the steps of history. By tracing the path from ancient censuses to modern cybernetics, we move beyond mere definitions. As we understand the why behind these discoveries, we master the very concepts we seek to comprehend.